Welcome to the second session of the Municipal Stormwater Conference. My name is Carla Malesi. I work with the Washington Stormwater Center and the University of Washington. And this session is called the Small Footprint Urban Retrofit Case Study for Municipal and Industrial Applications. And the presentation is going to be given to us by Bronwyn Rolph with Kennedy Jenks. And she is somewhat of a last-minute stand-in for Ross Dunning, so I don't have a whole lot of information to tell you about Bronwyn, except that she's been working in the stormwater world with Kennedy Jenks for approximately 5 years. Just a few notes that they will be recording this session. It's going to be about 20 minutes, and then we'll have some Q&A time afterwards, and the Q&A will not be recorded. And we're just asking everybody to please shut off their cell phones during the presentation. And welcome, Bronwyn.
I have to shut off my cell phone really quick. All right, so thank you for having me speak here today. Thanks to the Stormwater Center. I mean, these conferences are super invaluable for sharing knowledge. We all know stormwater is a relatively young field and how complex it's been getting. So this is a great opportunity to kind of learn from each other, and I'm excited to hear what y'all have to say today. As Carla said, my name is Bronwyn Rolph. I worked for Kennedy Jenks for 5 years, doing mainly stormwater work. We do wastewater, recycled water, a little bit of everything. But there's so much stormwater work going on in Washington that it kind of becomes a full-time job in itself. I'll be talking about a treatment system we did at the Port of Angeles. It is technically under the industrial permit, not the municipal, but there is a lot of crossover in the knowledge there. And you'll notice that I'll mention a lot. Maybe Kennedy Jenks provided the expertise or Kennedy Jenks provided the design, but a lot of this actually was Port implemented, which is pretty cool. It's kind of fun to work with a client that's so hands-on. And so a lot of what you're seeing here is stuff that any group, if you got the right equipment, anyone can do it. With that, I'll kind of jump into the project. All right, so Port of Angeles, it's on the other side of the peninsula, kind of due north in the center of the peninsula. The port was established in 1923. It operates 4 deep water terminals, and we're going to be talking about 2 specific sites today. The first is their marine terminal, including Terminal 3. You can kind of see down on the bottom side, let's see how well this clicker works. Down on the bottom side here, this is your marine terminal area, so you got some on-the-water property, some inland property, a good combination there. It's about 8 acres, and it's primarily log loading and then material storage. The second area we're talking about here is on the upper half of this photo. This is the cargo surge area. Similar industrial activities, a little less of that overwater work, but because they had such similar nature and kind of the activities being performed there, it became kind of logical to the port to handle this as one comprehensive area when it came to stormwater treatment. So before any of this kind of work was started, the port had several different areas that drained. You can kind of see 3 outfalls up here. Also see the deck drains along the dock area. And the first step, kind of precluding any type of stormwater treatment, was talking about how do you join that conveyance. And the reason that comes into play is it's very rare. We're very lucky when everything is conveyed exactly how you want it to be before you start thinking about treatment at a site. And sometimes reconfiguring that conveyance can be expensive, but occasionally there are opportunities where the cost of that reconfiguration is kind of outweighed by the savings you get in one centralized treatment system. So what was done at Port of Angeles is we kind of took an opportunity, we regraded the Terminal 3 area up here, had it drain back toward inland, plugged those deck drains, and created gravity flow kind of just right along the shoreline here in this marine terminal area. For those of you familiar with requirements for treatment of stormwater under the industrial permit, you don't have to treat every drop of rain that leaves your site, but you do have to treat the water quality flow rates, which is about 90% of the stormwater expected to come on the site. Most of your average storms are under that level. Occasionally, when you get a huge storm, you don't have to design to your 100-year storm. So we took advantage of that. First in this phase on the marine terminal side, putting in a flow splitter and a discharge opportunity over here. So calculating that water quality flow rate, what do we need to treat? What's above that? What can we let go? And doing a kind of a splitter system that allows that excess water to be discharged to the outfall. Following that, the remaining was pumped over, because there did need to be some active conveyance to get this water all this distance, pumped over to the CSA area here on the left, where it joined with gravity flow, another flow splitter, taking the combined flow rate and keeping that in one area and discharging the excess flows when they occur. So it's a little background now that we've talked about the conveyance is the water quality side of things. So the industrial stormwater general permit for Washington is pretty stringent. Industries are required to monitor once each quarter. There's parameters that apply to all facilities and then very facility industry specific parameters. And these are not easy parameters to meet. For those of you familiar with this permit, you know that already. The ones that we often see industries having issue with are turbidity, copper, and zinc, and that's any industry across Washington is sampling for those. And then logyards, in addition, total suspended solids and chemical oxygen demand. These are two parameters that once they're in the water, they're very difficult to get out, and if you have absolutely any industrial activity on your port, it's very hard to keep that out of the water. So Marine Terminal and CSA, there are no exceptions to this rule. They had a level 2 for copper, total suspended solids, and chemical oxygen demand, meaning that in one calendar year, for 2 quarters, they exceeded their benchmark requirements when sampling. And then they triggered a level 3 for turbidity in copper, which means 3 or 4 quarters they exceeded in these parameters. To give you an idea of what that looks like, turbidity is very low, 25 NTU. If you've ever looked in a glass of water and it looks at all cloudy, that's generally my guideline. That's about when you're hitting 25 NTU. Copper and zinc, both in the parts per million, 117 for zinc total, and in Western Washington, 14 for copper, 14 parts per million. And then finally, 100 milligrams per liter for TSS, and 120 milligrams per liter for COD. So these are very low numbers that these ports are trying to make, and any industries across the state. So looking at that, and looking at the fact that they did trigger this level 3, which requires treatment, the port started to think on a very specific level to their discharge. And so we worked with them on a bench scale test, taking effluent that's actually coming off the site, representative of what they're typically generating, and running that effluent through several different treatment medias on a small scale just to see the results and get a sense of what is the right treatment for this effluent. We ran it through sand filtration, Kytohan and sand filtration, biochar, and coagulant as well. And I should walk that back a little. Clearwater Services did the actual testing. I want to give credit where credit is due. Basically, the results from this indicated that passive biofiltration systems, so biofiltration meaning bioretention soil media, that's going to have your biochar, it's going to have your compost, and it's going to have your sand and your rocks, kind of that mix that's prescribed in the Stormwater Management Manual for Western Washington. That could be a viable option for actually removing the contaminants of concern in the port's specific effluent. You can kind of see here on the left, this is the water you're starting with, and to the right, this is post-decant, post-Kytohan enhanced sand filtration, and post-biochar. And you can see actually the biochar was probably the cleanest in this cup. But with a caveat, take everything with a grain of salt. You gotta keep your eye on the information because it changes. So the goal next was, we think biofiltration is a valid option. Passive systems are generally cheaper, generally less O&M over the years, so they can be a very desirable option. But they do often lead to a larger footprint. You're not pumping water through anything quickly, you're letting it gravity infiltrate. You're gonna need more space for that. So the next step was, can we minimize the footprint for this system? What can we do? Because for a port, land space is money. That's your operating area. What do you do to reduce the amount that you're infringe on the port's economic opportunities on their land? And so we did that with a pilot scale study. If any of you have maybe seen pictures like this before, it's done, kind of can be somewhat standardized. What was done here for the port, they set up 2 500-gallon totes, filled them with the exact same media layering you expect in the system, drain rock covered with 18 inches of bioretention soil mix, and used gravity by having a tank elevated above with the stormwater effluent. They controlled the flows, and they tested at 2 different flow rates, 18 inches per hour and 24 inches per hour. And they wanted to see, number 1, how effective is the treatment at each of these flow rates? And number 2, can the media sustain this flow through the media over time? Can we prove that we can be sending 24 inches an hour through this media? And the results looked pretty viable. So this is a lot of information. We don't have to go into all the details here, but if you look at these charts up here on the far left of each one, that's your benchmark, so that red line coming across. And you can see these effluent levels, and you see for turbidity, for total suspended solids, and for copper, they're getting effluents well above those benchmark values on the far left side. But the good news is, with each test they did, whether it be at 18 inches per hour or 24 inches an hour, they were finding that after they send that through the media, all of these numbers here were all below benchmarks, kind of further confirming that this is a viable approach. It's something they can do, and kind of giving some more data to support their decision on how they were going to proceed with this treatment. And that's just one. I believe they did 4 different storm events where they collected data. This is just one example of that. So to summarize it here, these numbers put a little more to it. For everything but chemical oxygen demand, they were seeing about 90% removal of contaminant, which is very good. The chemical oxygen demand, if you look back at that last slide, it may be more so that the COD coming in was not that high. They were already below benchmarks before they even sent it through the media. So less COD present in your water, less likely you're going to be taking a significant portion of it out. The other cool lesson they drew from this was, although there may be a small incremental improvement in 18 inches per hour, at that full 24 inches per hour, they were seeing pretty dramatic removal rates. These values were pretty comparable, and that made them feel good about 2 things. First, that they could pull forward with biofiltration, and second, that they could justify to ecology that they could size it for 24 inches per hour. I believe the SWIM standard for biofiltration mix, what they recommend is 12 inches, so they've effectively halved the size of their treatment footprint. And so that's what they did, and ecology approved it, which was exciting for everyone involved, because all of a sudden it means you're reducing your impact to operations. So after that, Kennedy Jenks, we designed a 3-stage biofill treatment system. So your first stage is over here. I have to speak into this mic, I'm told, so let's see if I can pop it out. All right. Your first stage is over here on the right. You've got your pea gravel, 18 inches. And this is kind of your first screening. You're taking out the big particles here. You're doing that with a really inexpensive media of pea gravel that if you're sending a lot of dirty water in there and you have to replace it frequently, you're not replacing that full biofiltration media. You're just taking the pea gravel out with a Vector truck, coming back, putting more pea gravel in. So this is your stage 1 of the biofiltration system. Stage 2, biofiltration treatment, exactly what was going into the pilot scale study, 18 inches of BSM media followed by drain rock. And then you'll notice here stage 3 is conspicuously empty. This was something the port could now do now that they had that extra footprint available, and they decided, let's see how this goes, let's see kind of what effluents we get after we install this treatment, and depending on what we find, we can tailor this 3rd polishing stage to be whatever we need it to be. Some of the benefits of this design, it's passive. So there is a lift station in this first vault that once that water quality flow rate is separated out, it is pumping to this first chamber. But after that, everything's gravity run. It's all hydraulically designed that it flows through. The bottoms of each of these vaults are sloped in the direction of the discharge pipe. So instead of having a bunch of perforated pipes down below that you need to occasionally clean out, just gravity does its work, goes down that slope and sends it to the area it needs to send it to. It's pretty easy to maintain. There are cleanouts in all of these perforated pipes. The biggest and most frequent maintenance is replacing that pea gravel, depending on, and it really depends on your site and what you're seeing for how often that has to happen. But it really is the work of a Vector truck in a day. And low wall height. One thing for the port, they want it to be something that's easy to inspect. Every time they drive by, they can see how the plants are doing. They can see if there's any issues, kind of just see the overall performance. And then no chemicals and low O&M costs. Once again, removing pea gravel is your biggest cost. You don't have to worry about any chemical calibrations, any balancing. It's all kind of a pretty natural process. So this design is, although it is, we always do something new and innovative with our designs, there is a kind of a precursor in the Port of Tacoma at their West High Levels logyard, which has achieved consistent attainment. For those of you not familiar, consistent attainment means they were below benchmarks for, it's either 8 or 12 quarters, and then they don't have to sample for quite a while that consistent attainment lasts, which is pretty exciting and pretty rare for a logging facility or a log handling facility. All right, so that's most of what went into the design process. I figured I'd show some pictures of the construction. give you a sense of what it looks like, and talk about a few more design elements through it. So here you can see the site. They decided to stage right over here. It's a little hard to tell in this photo, but this is kind of an outcrop area. You can tell it's vegetated. They're not currently sending a lot of traffic or operations out there, so it really is out of the way of most of their port activities. You can see it a little better. Right here, it kind of juts out. So they've got this kind of odd, awkward area on the outside they're not using quite as much. Take advantage, fit that treatment system in there. One thing the port did request, they wanted to be able to have continued vehicle access out in this area. If they ever do find they need to work with anything along the shoreline there, if they need to access the system from that side, they'll be able to do so. Just kind of giving them that ongoing flexibility that they're not building something they can't later get around if they need to. Thank you. Construction, so here the sidewalls are coming in. You can see, as I mentioned, so you can't really tell from these photos, but this is sloped, so that flows, once they trickle through the media, will be going this direction towards the discharge pipe in stage 3, which is then sloped this way and going out through that outlet chamber. And talking about redundancy, if you're a municipality, I know you like redundancy when you can afford it. It's always a good measure. One of the things we did was we did upturn 90s in each one of these inlet chambers. Which allowed that if there is an issue, if there is a reason flow is not going through as it should, or more flow than should be sending through there is being sent through there, rather than flood the system, you have an opportunity that this water level reaches this height, and it takes it out this pipe, and they've got a whole bypass system that takes it back out. So they can bypass large flows, not just from the pumping perspective, but within the system as well. Oh, and then one more cool thing is the pumps, as some of you may know, the water quality flow rate is not the flow rate you get in every storm. A lot of our storms in the Pacific Northwest, far less flow. We did variable frequency pumping so that on those low flow storms, they can send it in at a slower rate. Slower the rate, the longer the retention time, the better the treatment. Although, as we saw, even with 24 inches per hour, that treatment is looking pretty good. Media installation, if any of you are working on putting in biofiltration systems, the name of the game is not over-compacting the media. It's often put in, you can use excavator buckets and just have them lightly spread it out. Slingers are also often used by contractors to put it in, but your goal is you don't want to be compacting it much beyond, I think it's about 85%. You want to let that high flow rate through if you're going to be fighting for something close to 24 inches an hour. And this is a couple examples of the project complete. As you can see, the plants are taken off pretty well. One interesting thing about bioretention is plants can assist, but it does appear, based on what we've seen, that the BSM material itself is, even with no plants in there, is doing quite a bit of work on its own. So challenges and results. Some of the challenges for the industrial permit, they require very quick timelines for turnarounds of treatment systems. Now, many industries will pursue a waiver that gives them more time so they can do this front-end work to pick something that's effective to their specific site. But even with that, everyone is always trying to turn things around quickly. You've got to get that system in by the time that administrative order requires it. Other issues, it's still a business. Tenants and ship loading and constructing around that, it's an ongoing discussion of how do you phase a project so you don't impact the commercial side of the site. Operator strikes, it's also very difficult to get your staff to work with you if they're on strike. We did have some issues with the BSM mix when infiltration testing in the first go-around, and that was primarily an over-compaction issue. So once again, there's two things important with biofiltration and BSM. First being making sure the compaction is not over-compacted. Second being quality control on what you're getting on site. You just want to make sure that everything you're getting is actually meeting your spec. They are still working on turbidity and copper, and this is more common than I'd like, that you can do a pilot scale with your effluent and then you can put it in the field and it operates a little differently, and that's just kind of the name of the game. But with their stage 3, number one, they are working on all the things they can do to improve that treatment rate, and they are now looking at, for stage 3, what are the appropriate things to bring those copper and turbidity levels down to the levels they want them to be. So I would be remiss if I didn't thank the Port of Port Angeles. We've got some pretty great people over there. They're very hands-on, did a lot of this pilot scale and everything else themselves. And it's been a great opportunity to work with them on this project. And with that, are there any questions? Yes?